In this second video tutorial, we're now going to start melting our ternary systems. And we're going to have to look at solid-liquid equilibria. Conceptualizing these diagrams can now get a little bit tricky, as we're going to have to use 3D space diagrams. So here we'll do that, initially focusing on 2 and 3 phase equilibria. When we consider melting in a ternary, we're going to have to develop some new ways to portray the phase behavior in the system, because temperature necessarily is critically important, and we can't rely on isothermal sections as we did in the solid state equilibria. So how do we represent melting behavior in a ternary system? First of all, there are space diagrams. These are three-dimensional constructs where still our composition is represented on the basal triangle, but now we've added the temperature component in this direction, and our diagram to represent the phase behavior at first looks very intimidating, but hopefully in the first part of this video we can make them somewhat understandable. We can also use so-called Liquidus projections, where the melting behavior is projected on the basal triangle. And we'll look at a variety of examples of Liquidus projections, beginning hopefully with some more simplistic systems, but then building towards looking at a rather complicated ternary, in this case the MgO-SiO2-Al2O3 phase diagram, which contains a wealth of detailed information. And we'll be using all of these to quantify solidification paths of certain overall compositions in the system. So let's begin with the simplest type of system, where all of the component binaries are ideal and we have complete mixing in the solid and liquid state. In other words, we have the familiar looking binary phase diagram with our liquidus and solidus loop. So now let's build a space diagram for the system where we take the three ideal binaries and look at the changes in behavior with temperature. And in this case, we're going to get a liquidus and solidus surface. So let's just take a second to look at this diagram so we're on the same page in terms of understanding what I'm representing. So here's my AB ideal binary with my solidus liquidus loop. Here's the one in the BC system, and at the back the AC system. But now instead of just having a solidus line, we have a solidus surface. A three-dimensional surface along which the solid composition lies when it coexists with the liquid. And the liquid lies on the liquidus surface shown in blue here, this curving surface. The enclosed space between the two is our two-phase region where the solid and liquid coexist. Let's just take a vertical section through these two surfaces to see if we can understand what's going on in 3 dimensions. So now if my overall composition is here, when it hits the liquidus surface, that liquid composition coexists through a tie line with a solid composition that lies on the underlying solidus surface. As we cool, the liquid follows some path on the liquidus, the solid does the same on the solidus surface, and a vertical section would look something like this. Here's my overall composition. This is then temperature in this direction. Here's my liquidus surface projected, here's my solidus surface projected, and the compositions follow the two respective surfaces. And they're joined at any particular temperature by a tie line. There are several real phase diagrams that look like this. An example is the palladium gold silver system, where all of the binaries are ideal. Here's the palladium silver one. Palladium melting at the higher temperature. Here's my liquidus solidus ideal solution loop. Now we'll make it a ternary system, so I'm going to fill in the basal triangle by adding silver at the bottom. The gold silver binary, it's also ideal, and the silver palladium binary, also ideal. So here's my 3 component binaries. Now I fold them over if you like, or bring them together in the space diagram for the ternary system. Let's put that together. Now let's just get rid of those 2 binaries. There's my solidus surface, and on top we'll add the liquidus, just as we did before in blue. Quite often, liquidus isotherms have been determined experimentally and then added to the diagram. So here I'm adding these isotherms, 1500 through 1100, and so anywhere along this isotherm, then when my overall composition cuts through that, crystallization would begin, for example in this case, at 1500 C. What we can do to make this slightly easier to work with is project all of the liquidus isotherms onto the basal triangle. And when we project that liquidus information, that's called a liquidus projection. So let's project those isotherms down on the basal triangle. Let's get rid of the two surfaces. And this would be the liquidus projection for my palladium gold silver system. So here are my contours of temperature, the contours along which a solid would first appear. Let's pick an overall composition and quantify the beginning of solidification. For example, this one. We see this composition then would start to solidify at 1300 C. And we will start to use these liquidus projections quite extensively later on to look at crystallization paths. We could also take an isothermal section through the space diagram to look at what is happening at a given temperature during the solidification process. So for example, let's take an isothermal section here at this temperature T1 that cuts through the liquidus and solidus. So we're cutting through here in my projected view, and let's draw that isothermal section. These can get a little bit tricky to draw, but let's just see if we can understand what we're representing. So anywhere in this region shaded in blue at this temperature, the three-component alloy would be all liquid. In other words, we're above or outside the liquidus surface. Then as we cut through the volume in between the liquidus and solidus surfaces, we'd have a two-phase solid plus liquid mixture. Then as we come through that region at these compositions, they would be all solid. So I have an all solid region, all liquid region, and a two-phase mixture in between them that is solid and liquid lying in this region of the volume here shown. And we can add the tie lines that would connect the coexisting solid and liquid compositions. So it's possible to sketch and draw a whole series of isothermal sections at different temperatures to map out sections for any temperature that one desires. We're not going to focus too much on these, however, as you will see later on. I think the liquidus projections are much easier to work with in predicting the quantitative solidification of different overall compositions. Okay, let's ramp up the complexity a little bit by now looking at a ternary system where two of the binaries contain a eutectic and one of them is still ideal. So in this case, I've made the AB binary have a eutectic with some solid solution on either side, an alpha region solid solution and a beta region based around B. Here's my eutectic liquid in the binary. Then in the BC system, we have another binary eutectic. In this case, I've made the eutectic temperature in this system lower than it is in the AB system. And finally, we'll say AC is ideal. Bring the three together and we'll get the space diagram. So let's do that. So here's the AB binary, the eutectic, with the coexisting solid and liquid compositions at that binary eutectic shown and denoted by the letters DME. Here's my BC eutectic, now shown on this side of my space diagram. And finally we'll add the AC binary here, it is ideal. And so now we're building up the ternary space diagram. So we'll just fill in the rest of the solid state behavior. In this region, this is single phase beta. Out here, it's single phase alpha. In between the two in the solid state, I'd have alpha plus beta. So now let's identify and label some key features of this space diagram. First of all, let's take a look at the eutectic valley. And we can use everyday geographic examples just to conceptualize in 3D what is going on here. So the eutectic valley is the composition of the eutectic liquid that runs from that higher temperature AB system at M down towards the lower temperature eutectic in the BC binary at N. So let's join it. Here's the liquidus composition, or the so-called eutectic valley, and my arrow indicates that we're going down in temperature. We have two liquidus surfaces now. Let's highlight those in blue. First, I have the AMNC surface, shaded here, and then also the BMN surface, curving down in this direction. Now let's identify the two solidus surfaces. Shade them in yellow. First of all, we have BEF. If my solid composition lies on this surface, the solid is beta. The other solidus surface, sort of wrapping underneath this liquidus surface, is ADGC, shaded in yellow, and that would be associated with primary phase alpha. So let's just fill those in. What's new here? Two liquidus surfaces, each identified with a primary solid phase, alpha for AMNC, beta for BMN, and then a eutectic valley along which the composition of the liquid must lie. Just highlight the three-dimensionality. I've added a potential overall composition here in orange. We'll deal with this in a second. But in this case, as I cooled, then my sample would first hit the BMN liquidus, which is associated with primary beta, and the solid would be constrained to the beta primary phase surface, and the liquid would run down this liquidus surface. When the liquid reaches Mn, we will now have a three-phase equilibrium between alpha, beta, and the liquid. Let's take a look at how we represent that. Now the liquid has reached Mn, we will have this eutectic reaction, where it's in equilibrium with alpha and beta. Alpha must lie somewhere along DG, and beta must lie somewhere along EF. And as we mentioned, the liquid is lying along the Mn eutectic valley. When we have a three-phase equilibrium, we've seen before, for the all solids, we use tie triangles. And we'll do the same here, except now one of the coexisting phases is the liquid. So in this case, alpha is along DG, this vertex of the tie triangle, beta along EF, and here's my eutectic liquid lying somewhere along Mn. Now actually, Mn, DG, and EF are not coplanar. To clarify that, let's look at this vertical section where my temperature is decreasing down the slide. So in this sketch, this is the AB binary, this is E, M, and D, the three phases that would participate in the eutectic reaction along the AB binary at the back here of the space diagram. On the right-hand side in this section, I'm drawing the corresponding eutectic in the BC system. So this would be composition G of alpha, N is the composition of the eutectic liquid, and F is the composition of beta along that binary. Now in this perspective we can see that this liquidus line, the eutectic valley, actually lies above the plane of EDFG. Let's use our tie triangles to show the progression of solidification as I go into the ternary system and cool. So for example, if I was cooling a composition undergoing this reaction, then the compositions of beta and alpha are coming down their respective lines. The liquid is doing the same along Mn. And now I'm using an isothermal tie triangle, the composition of alpha, beta, and liquid at the vertices will cool down, the triangle will shift, the compositions moving along their respective lines. So here's a lower temperature, again an isothermal tie triangle, but we're at a lower temperature. Keep on cooling. Here's another isothermal tie triangle again showing the progression of this liquid down Mn. So I hope this gives you some sense for the dimensionality of this three-phase space. Let's use the space diagram to look at the crystallization path of a composition. We'll choose this one here that cuts through this BMN liquidus. First, let's just check out our final product. So after all is said and done and solidification is complete, if we look at the basal triangle and the solid state equilibrium, we see it lies in a two-phase alpha plus beta region, and that is highlighted here, just adding the tie lines in that solid state two-phase region. So that's where we're going to end up. How do we get that? Well, first let's look at the primary phase. X cuts through this BMN liquidus, and that is associated with the beta primary phase. The composition of beta must lie on this BEF surface. And so what I've done here is add a tie line that shows what the composition of that first beta phase would be when the liquid hits that liquidus surface. Now, as we keep cooling, the liquid will move down the liquidus surface towards the eutectic valley, and correspondingly the composition of beta will move down the beta surface, ultimately reaching some composition along this EF line. Once the liquid reaches the eutectic valley, then we're going to use tie triangles to represent the three-phase equilibrium, because now, once we partake in the eutectic reaction, we don't just have liquid and beta anymore, we start to form alpha with a composition on this DG line, and the compositions of the three phases lie at the vertices of this tie triangle. Now in my lower right, I'm just pulling out that first tie triangle. When the liquid first reaches Mn, I have a two-phase coexistence of beta and liquid, but now the composition of the liquid is moving down in temperature, down Mn. The composition of beta is moving down EF. Alpha is forming, and as I keep cooling, its composition will move down DG. And so if you can imagine that this tie triangle moving down, X is going to shift into the tie triangle. Let's take a look at that. So here we'll highlight the movement of the tie triangle for this three-phase crystallization, where it's a eutectic, alpha plus beta in equilibrium with liquid. All of my compositions, beta, alpha and liquid, they're constrained to their various lines, and the tie triangle will move in this direction. And as the tie triangle moves, why is it moving? Because the compositions of the three phases are moving to lower temperature. Then ultimately X will end up lying on the alpha beta side of the tie triangle, and at that point the liquid is consumed. During the crystallization, as the tie triangle moves X from its original position along the beta liquid line to its final tie line along alpha beta side of the triangle, we can map the percent liquid if we wish to do so when X is lying within the tie triangle using the lever rule. We can also map the crystallization of that composition using the liquidus projection, where I'm projecting the solid and the eutectic liquid compositions onto the basal triangle. And I've done that here on the left. Here's DG, the composition of the alpha phase that participates in that three-phase equilibrium. Also the same along EF for beta. So this is single-phase beta over here. All on this left side it's single-phase alpha, in between my solid-state two-phase region. And here is my liquidus projection, where I'm projecting that eutectic valley that runs from M down to N. Here's my overall composition, shown in orange. Let's map the crystallization using the tie triangles. Initially, I form beta, and when L reaches Mn, the composition lies along that beta liquid side of our tie triangle, along that tie line. Now we keep cooling, the tie triangle is going to move down in this direction. There it is, we've moved it down a little bit. Composition now lies within the tie triangle. Three phases coexist, and they will keep coexisting until the tie triangle has moved to its final position along the alpha-beta tie line. There is no liquid left, and the crystallization is complete. Let's go to another type of space diagram that we can find in material systems that are melting or crystallizing. In this case, let's look at a three-phase equilibrium that involves peritectics. Now, we'll say that my AB binary has a peritectic reaction, so the liquid here lies outside the two solid compositions, alpha and beta. And we'll say that the AC system also has a similar peritectic, shown here. Here's my liquid peritectic in the binary, lying outside the two solid compositions, alpha and beta. And we'll assume that BC has complete solubility. So this is ideal, complete solubility of beta. So let's fill that in. There's the three constituent binaries. Let's join up some of the lines and add the peritectic liquid that starts in the AB binary and ends up in the AC binary, running down in temperature in the direction of the arrow. Let me just add some lettering to denote the various compositions of the phases that participate in the reactions. For the AB binary, M is the peritectic liquid, E and D are the compositions of alpha and beta respectively. For the AC binary, N is the peritectic liquid, F and G are the compositions of the coexisting alpha and beta phases. In the middle of the system, we still have a peritectic reaction. Alpha plus liquid is in equilibrium with beta, but the liquid could be anywhere along Mn, and the two solid compositions could be anywhere along EF for alpha and DG for beta. Alright, let's colour in some of the liquid surfaces just to give you a sense for the 3D nature of this system. So what I've shaded in blue are the liquidus surfaces. AMN, that is the liquidus surface that's associated with primary phase alpha, and BMNC is the liquidus surface that we'll find is associated with primary phase beta. Again, let's just use an everyday, if you like, geographical example so we can conceptualize this. So here's my peritectic valley. It's not quite a valley, it's a perturbation on that liquidus surface running downhill. And so I'm illustrating that with this train here, where the tracks have been built halfway down the mountain. It's running down the mountain in that direction, but here's one surface to the right and one surface to the left, just like that. That's a three-phase peritectic. Let's shade in the solidus surfaces. Underneath this, DGBC, that is the beta solidus surface associated with the liquidus surface BMNC. And on this side, AEF, let's shade that in yellow, that's the alpha solidus surface. That's where my primary phase alpha, and it would be coexisting with the liquid that is on the AMN liquidus surface. DG lies below EMNF, so again I have a three-phase space bounded by the surfaces shown here. The easiest way to highlight this is to just look at an example of a crystallization, and the one I've shown X, we can already see where it would end up at the lowest temperature. Where does it lie? It lies in a two-phase alpha plus beta region. So after all is said and done, this will crystallize to a two-phase solid mixture. But exactly how does it do it? What is the path of the liquid? Let's go to the next slide to take a look. Let's have a look at the liquidus surface and see where X cuts through it. We can see that X is going to intersect the AMN liquidus, and the primary phase for this liquidus is alpha. So alpha lies on AEF. Let's just add a tie line that connects those two coexisting phases. So the first composition of alpha that's formed is shown here, and this is my liquid composition on that Liquidus surface. We're cooling, so now alpha is going to move down in this direction on its Solidus surface, and the liquid will roll over the Liquidus surface towards Mn. Let's show a couple of arrows showing the direction of their movement. When the liquid reaches Mn, now we're going to have a three-phase equilibrium. So we don't have just alpha and liquid anymore. This is going to be the temperature at which beta first forms. And when three phases coexist, we don't need tie lines, we need tie triangles. So let's add one. So when I first reach the peritectic, where the liquid first reaches Mn, this is my liquid on the right. This is that alpha composition. It came down its Solidus surface. Now it's somewhere on this line EF. And we're about to form a new phase, beta, and beta at the other vertex of the tie triangle will lie on DG. Let's blow up that tie triangle so we can show it a little bit more clearly. Here's what I just described. At this point, the liquid's just reached Mn. X is along that tie line, alpha liquid. We haven't formed any beta yet, but we're about to do so because the liquid will move to lower temperatures, as will beta and alpha. That movement of the tie triangle in the direction of the arrows, X ends up in the middle. Three phases coexist. This triangle will keep moving, and eventually X will end up on the alpha beta side. And at this point, the liquid is consumed and the solidification is over. Well, again, we could use a Liquidus projection to monitor that crystallization path. Let's map the key features of the space diagram onto our basal triangle using the Liquidus projection. So here's Mn, my peritectic, not quite a valley, but that was the movement of the train down the hillside, if you remember that. That's the train on these tracks going from M down to N. And when three phases coexist, alpha must be on EF, beta must be along DG, and of course in the solid state between these two I have a two-phase alpha plus beta region. When we're using a Liquidus projection, the first thing we should do is label the primary phase fields on this projected view. AMN is primary phase alpha. So here's A, here's M and N on my projection. So I'm going to shade that in. That's my projected alpha primary phase field. If my composition lies anywhere in this blue region, the first solid phase to form is going to be alpha. Beta primary phase field, that's when the composition lies in B, M, N, C. Let's shade that in green. So this is the beta primary phase field. Here's my overall composition. We see two things. Number one, when we end up, it's two-phase alpha plus beta. But we also see that the first surface it intersects is the alpha primary phase field. And that's pretty clear from this Liquidus projection. If we're pulling out alpha from this overall composition, so alpha lies over here, the composition of the liquid must move in the opposite direction. So the composition of the liquid follows a straight line path over the Liquidus surface to Mn. Then when the liquid reaches Mn, I have a three-phase equilibrium. So we're going to use tie triangles. Let's add our first tie triangle. This is the liquid composition. This was alpha. And now I'm crystallizing a new phase, beta, somewhere along DG. I'm going to put it right here. We can see our overall composition lies on this side of the triangle. So right now, we don't have any beta. As we cool, beta forms, the tie triangle moves down in this direction, and we can add a second triangle that shows when the crystallization is complete, then it will lie along the alpha beta side, and there will be no liquid left. And so that's my completion of the reaction, where the last tie triangle before crystallization is complete is the one shown. Here's my liquid composition, here's my beta composition lying along DG, and here's my alpha composition lying along EF. Next, we need to consider what happens when four phases coexist. and we'll do that in our next video.